Hello, today's topic of the lecture is about carbons. Okay, so we'll discuss our structure of carbons, then their uh, stability and the generations, and as well reactions like this. So first, let us see the introduction part of carbons. So what are carbons? Carbons are generally unsourced or unsourced species. Okay, unsourced divalent species, divalent having two valence electrons, divalent sextet species, sextet in the outermost shell. That is, they have six electrons in the outermost shell. Okay, so they are electron deficient species. Electron deficient species. So what I'm telling is that elect so that the carbons are uncharged divalent like this. They can have divalent. So like this. Just say A, B, or you can say RR also like this. So they have divalent, two electrons, and they're having six after 1, 2, 3, 4, 5, 6, 6 electrons. So are deficient, electron deficient to get the octet in the outermost shell. Okay. So carbons are uncharged divalent, highly reactive species. Reactive species intermediates. Okay. So now carbons can have two types of uh, structure. So they can have singlet, can have two types. Okay, singlet carbons. Another one is separate carbons. Okay, separate carbons. Depending on the nature of the electrons, here these two electrons might be paired or spin paired, or another one might be spin parallel. So in the case of singlet carbons, they are spin paired, spin paired, spin paired. These are the electrons are like this. Okay. In the case of the carbons, the spins are parallel, parallel. The spins are parallel. Okay, parallel. Not not paired. So like this. Okay. So that can be differentiated. In the case of singlet carbon, the two spins are paired, and they are having the spins are having is zero. The total spin is zero. In the case of separate carbons, the spins are parallel, and the total spins of the separate carbon is one. That is paramagnetic. Spin is one. Total spin of singlet is zero. Total spin of separate carbon is one. So it is paramagnetic. They are paramagnetic. So separate carbons are paramagnetic. Okay. So this is about the difference between these two types. So what I'm to say that carbons can have two types. One is singlet carbons, another one is separate carbons. In the case of singlet carbons, the two spins are paired in the case of separate carbon, the two spins are parallel. So they are paramagnetic. And the total spins of singlet carbons is zero, while total spins of separate carbon is one. And separate carbons are generally more stable than this single carbon. Okay. Now let's see about the structure of carbons. Okay. Let's see the structure of carbon. We can have these two structures of singlet as well as different carbons. So let us see the structures of carbons. Okay. So we can discuss one by one. So let's first discuss the structure of singlet carbon. Singlet carbon. Okay, the structure of singlet carbon. So we have to now that singlet carbon is like this. They are paired and A, B. Okay, so you can write this singlet carbon A, B like this. Okay, it can be represented like this. So structure is like this. They are paired structures. These two p0 orbital, this sp2 orbital, and this is A Okay, the angle is 103 degree and angle between this is 103 degree. So this is 2pz orbital. It is empty 2pz orbital, and this is sp2 orbital. Okay, so here the two electrons, the two spins occupy the sp2 orbitals, and they are having empty 2pz orbitals. So this is the structure of singlet carbene. This is that they have band sp2 hybrid structure. Okay, they have sp2 hybrid structure, which is also planar. Okay, so so I'm repeating again. Singlet carbenes are having band sp2 hybrid structure and planar, and then the two electrons, the two spins occupy the sp2 orbital, and the 2p orbital is empty, and the angle between these two bonds is 103 degree. So now let's see about the structure of triplet carbene. Okay, now let's come to the structure of triplet carbene. So triplet carbenes, here two spins are parallel. So let's see structure of triplet carbene. Okay, triplet carbene. So here similarly here also like this, we have C, like say here A, B, and this one spin is like this. You can write this way also, no problem. Like this, A, B. Okay, so these are parallel. These two spins are parallel. Okay, so they are paramagnetic. The structure is, they can have two type structures. One is band, the earlier one, single type. So here, but here the angle is between is 136 degree. Okay, and this is the sp2 orbital, and this is 2p orbital. Okay, 2p orbital. So here the two electrons occupy each of this orbital like this. So here similarly here also band structure is band sp2 hybrid structure. Having it is also planar. Okay, planar like singlet one, but the only difference is that here two electrons occupy each of these 2p orbital and the sp2 orbital. Here the 2p orbital is not empty. So it is about another type is for the triplet carbene. They have another type is linear one. Okay, A, B, this here being linear one. So here they have sp hybridized. Okay, these are p orbitals. These are p orbitals. Okay. So the p orbitals. So here the two electrons occupy each of these p orbitals like this. So they are parallel, and angle between these 180 degrees Celsius. 180 degree. Okay. So 180 degree here. So this is here linear sp hybrid structure. Okay, hybrid structure and linear. It is linear planar here. So what I want to say now, I'm repeating again. In the case of structure of triplet carbene, that they have two types of structure. One is band sp2 hybrid structure, and another one is linear sp hybrid structure, sp. So in the case of band sp2 hybrid structures, the two spins are occupied each of this sp2 orbital as well as the 2p orbital. So in the case of linear, each of the spins occupy each of the 2p orbitals like this. But generally by experimental studies, it is found that this structure is more favored and is mostly found in most of the triplet carbenes. They are stable and they are found in the ground state. Okay, so this is about the structure of this singlet and triplet carbenes. Now let's come to generation of carbenes. How carbenes are generated. So let's come to generation of carbenes. Okay, There are many types where the carbenes can be generated, but there are the two main types of actually there are two main types of for generation of carbenes. First one is by thermal or photolytic photolytic decomposition of decomposition compounds compounds containing containing certain double bonds, okay, containing certain double bonds. So this is one main type. So they are generally double bonds. So the first one is there are two main types of for the generation of carbenes. First one is by thermal or photolytic decomposition of compounds containing certain double bond compounds. Okay, so generally we can represent like this: either heat or light. Okay, photolysis, thermolysis, or photolysis. So this suppose the RR. So you can have this carbon. Okay, RR carbon plus X like this. So this is a certain double bond depends on this X. So you can have depend the type of double bonds. So this is first one. So one main types of reactions. So I will give some examples. Say from diazomethane. So so carbenes can be generated from diazomethane by photolysis as well as or pyrolysis. So first, so in the from diazomethane, okay. This is from the past type, one type from the past type. So we have sub headings also, like from diazomethane is double bond, different double bond they can have as like this. Okay, you can have like this diazomethane, or you can this structure like this. So you can have like this, okay, and positive charge and negative charge like this. This is diazomethane, okay. So diazomethane can be just by heating or by pyrolysis. We can have again these carbenes can be generated just by heating or by photolysis. So you can substantially you can write this is CH2 and 2. This is diazomethane, heat, or this is like photolysis or heating thermolysis. You get this carbon plus nitrogen. Okay. General mechanism is like this. So here this is okay diazomethane. So you can write this way, or like this. So this you can get this. Let's say H2, H2, carbon plus nitrogen. Okay, this is nitrogen now. Or from this structure, similarly you can have this one, same case, same one. Okay, these are. So here, if you remove this one, remove, you can get this same product. Okay, you got this one. So two ways you can have that. So what I want to say is from by heating or by photolysis, by thermolysis or photolysis, diazomethane can give carbon as by removal of nitrogen. Okay, so this is for certain double bonds. They have certain double bonds like this, and another one is from ketenes. Okay, another one is from ketenes. See, another one is from ketenes, another double bond types. I'll just show this one from ketenes. So like C, that one's okay, like this. So you can have here also like RR or like this. So generally by photolysis, ketenes on photolysis, they lost this like this. Okay, they kept RR, this carbene, and plus carbon monoxide. This is carbon monoxide. Okay. So here also certain types of double bonds, compounds having certain types of double bonds, they can have generated carbons. So I'm giving from diazomethane, ketenes. There are another many other reactions also there. So we can have from epoxides, another one from epoxides and cyclopropanes. Okay, this can be generated from cyclop. So these ketenes can be, okay, carbons can be generated from epoxides as well as cyclopropanes. So for example, this epoxide is having this, it's substituted with phenyl, CN, let's say. So you can have these types of, so you can generate like this, see like this. Okay, so this is by photolysis. So epoxides can be can generate carbons, okay, like this. Plus this is benzophenol. Okay, so I'm giving one examples from epoxides. Just by photolysis, by photolysis we can get this carbene and then this benzophenol. And from cyclopropane also I can give one examples. I'm giving one example here. See cyclopropanes. Okay, let's say CH2 here. CH2 and these two are phenyl. Okay. So by photolysis they can generate this. So here also same case, you can generate this one. Okay, either this way. You can have here or here, the same case. This way or this way, okay, same case. So here you can get the double bond here. See double bond, CH. This is phenyl, and plus this is carbon. Okay, CH2 carbon. So it is another way for generation of carbons. So I'm here explaining about from epoxides and from cyclopropanes. By photolysis we got carbons. Okay. The another one from another method is from diazidine compounds. By photolysis of diazidine compounds. Diazidines are like this, cyclic compounds. These diazidines, you can have this RR. This is diazidine. Okay. But by photolysis, so you can get this one, okay, like this. So you got carbene, you got carbene plus this nitrogen. Okay. So this way, but diazidines can be obtained from, diazidines can be derived from diazidine, and then diazidines are like arsenate, this one, NAs, and this one, the diazidine. This also can be again prepared from these ketones, by reacting with ammonia, like chloramine, say like NH2Cl, chloramine, NH2Cl. This is called chloramine. Okay, so what I want to say that these carbons can be generated from diazidine by photolysis. So but this diazidine can also be obtained by from ketones by reacting with ammonia and chloramine to get the diazidine, which is oxidized to, which can be oxidized to diazidine. Okay, oxidized. So it's another method for generating the carbons. So we have discussed the past main type is by photolysis or thermolysis of certain compounds containing certain double bonds. Compounds containing certain double bonds. Now second type is second types of generation, second main types of generation is from by one second type, okay, by alpha elimination, by alpha elimination, by alpha elimination. You can say one elimination. Okay. So what is the one elimination or alpha elimination? Alpha elimination or one elimination is that if the two groups or are removed, so let's say from the same carbon atom or same atom, if the two groups are removed, eliminated, so by base or like this, okay, then you got this carbon, okay. So if two groups or two atoms are removed from same carbon atom, then it's said to be alpha elimination, or you can say one, okay, same carbon atom. But beta elimination, it is different from beta elimination. But in the case of beta elimination, two groups or atoms are removed from the recent 1, 2, okay, 1, 2. So this is called beta elimination. So like this, pairs are select. So difference between these two. So here in the case, so this is called 1, 2 elimination or beta elimination. But carbenes are generated by alpha elimination, not from beta elimination. Whatever. Just comparing these two. Okay. So many examples are here in the case of alpha elimination. So one is from chloroform. Okay, chloroform, you know, chloroform, CaCl3, CaCl3 is a chloroform. So react with sodium hydroxide, the alkali with the stars, okay. First step is this alkali, this extract the proton to give a carbon ion, here. Carbon ion is obtained. Then loss of this chloride, taking this one, okay. So here 2 electrons are given here, okay. So here, so you can say 2 electrons are given. You can write this way also, like this. 2 electrons are here and negative charge. So negative charge taken by chloride, so it becomes so like this, chloride, this carbon plus Cl negative charge, okay. So this negative charge taken by chloride, so this is carbon. So this is by removing of one hydrogen and one chloride, so you got this carbon alpha emission. So from same carbon atom we remove hydrogen, two atoms are removed, so this is alpha emission. So this is the best. So this mostly carbenes are generated by this method. So we have discussed these two main types. One is by thermolysis or photolysis of compounds. First one is compounds containing certain double bonds, and second type is by alpha eliminations, by or by 1, 2 eliminations. So this is about the generation of carbene. So next I will discuss about. So next we discuss about this reactions of carbenes. Carbenes generally can have two types of, okay, can you see, I can just show you reactions of carbenes. Okay, I just reactions of carbenes. So here we can discuss two main types. One is insertion reactions. One is insertion reactions. That is, and second one is addition reactions. So these two types of reactions of carbenes can take place. So here insertions to CH bond, okay. Insertion of carbene to CH bonds. Insertion of carbenes to CH bond, and here addition of carbenes to multiple bonds. You can say the olefinic bonds, CC double bond like this. Okay, the CC double bonds. So these two types we will discuss one by one. So here carbenes can undergo two types of reactions. One is insertion reactions, another one is addition reactions. So let's see one by one. So first one we will see insertion reactions. So carbenes can undergo insertion in between these carbon hydrogen bonds. Okay, insertion reactions. So carbons can insert carbon can insert into the CH carbon hydrogen bonds. Okay. So for example, many examples are here. For examples, so let's say hydrogen here, CH3 here, another ethyl group here, CH2 CH3, another ethyl group, here, CH2 CH3. So when you react with carbon, so let's say methyl and carbon, okay, this one. So you can insert this here, pass here, let's say this in between this CH bond, you can have CH3, another one is the untagged, other untagged CH2, you can say ethyl, this ethyl, okay. So pass one instead. Then you can get another product also here in between these two, this here, so many CH3 are here. CS bonds are here, CH like this. So you can have another product. So I can write here, okay, C hydrogen here, this one intact, and this one CH2, CH3, okay, this is ethyl. So here another one is inserted in between these two, and here also you can many products you can have. Here also inserted here, hydrogen here, CH3 here, this is ethyl group is intact, and so here CH, another one here, so you can have CH3 and this CH3, okay, like this. So similarly you can have so many products, so many products of them. Yeah, because there are many CH bonds are here. There are so many CH bond here, CH bond here, CH bond here, CH bond. So you can have many products. So in the case of insertion reactions, carbon insertion reaction is not very good for these synthetic compounds. In synthetic organic chemistry, this type of carbon insertion reaction is not so important because you got a lot of mixtures of products are obtained by reacting. So let's see the mechanism of the insertion reactions. Mechanism of insertion reactions. Actually, carbon can insert by two mechanisms. So that's the mechanism of insertion reactions. Mechanism. So there are two types. One is concerted mechanism. Another one is free radical mechanism, okay. Or you can say radical mechanism. Free radical mechanism. So in the case of insertion reactions of carbons can undergo two types of mechanism. First one is concerted mechanism, and the second one is free radical mechanism. Now let's see first type, concerted mechanism. So let's see in the case of concerted mechanisms. So here like this. This is the CH bond, okay. So we have this carbon, okay, like this. So you can have concerted like this, okay, this one or this one like this. So through some intermediate goes through some intermediates. See, so like this, okay, this is concerted. So your product will be C111C, and then we have C, okay, hydrogen like this. If you have this hydrogen, two hydrogen here, then you can have methyl and carbon, then you can have this similar CH3, okay. So this is the past method is uncertain mechanism. So you can have through the intermediate, so you can have direct insertion takes place from here like this. And in the case of second type is free radical mechanisms. You have two steps. There are two-step mechanisms. So let's see radical mechanism, okay. B, radical or free radical mechanism. Free radical mechanism, okay. Here same one. Okay, let's see. This is the cis bond plus this carbon. Okay, cis carbon. So like this carbon have like this. Okay, so first one is this one goes like this, and this one electron has gone, and this another electron has gone like this. So first step is this is first step, formation of radicals. Two radicals are formed. So they have one plus. This is another one. This is a 3R group. Now you have 3 hydrogen atoms, and this one radicals. And second step is combination of this, is dimerization of this two electrons. These two spaces, two radicals are now combined together. You can say CH3, you can write this CH3. So like this. So yeah, like this combination takes place to give this product. Okay. So in the case of radical mechanism, you can have two steps. First step is formation of two radicals like this, and then the termination, two radicals are combined together to get this like this. So this is about insertion reactions of carbon to CH bond. So you can have two types. One is insertion reaction of carbons is two types. One is concerted mechanism, another one radical mechanism. Now let's come to addition of carbons to double bonds, olefinic double bonds. Okay. Second type is addition of carbons to carbon-carbon double bonds. You can say olefinic compounds to carbon-carbon double bonds. So you can have double bonds. The carbon, let's say Cl, another carbon, Cl. So you can have two types of, now we can have two types carbon. So you can have a cyclic structure, you can have Cl, okay. So you got a cyclopropane, So when carbons are added to olefinic double bonds, you got a cyclopropane. So the whole process you know is cyclopropanation. Okay. So addition of carbon to the carbon-carbon double bond is carbon-carbon double bond is known as cyclopropanation because cyclopropanes are formed. So depending on the nature of this carbons, so we can have either singlet or triplet. So addition can take place two types. So I'll show you this how take place. Okay. So addition of singlet, there are examples. Okay. Methyl group, another CH3 methyl group by singlet carbon. This is singlet carbon. Okay. Singlet carbon. So when singlet carbon is added to cis, okay, this is 2 cis2 butene. Okay, 1 2 3 4 cis2 butene. This cis2 butene reacts with singlet carbon. You got a propanol, cyclopropanol, Cl here, and this is hydrogen here, hydrogen here. What I want to say, what I want to say is that cis addition of singlet carbon will give cis cyclic product. Okay, cyclopropane product. Cis will give cis, and trans will give this methyl group. Okay, this is methyl group, Me3, MECH3. Okay, this is trans. So here singlet carbon, okay, carbon singlet carbon will give the product will be also trans product. Cl is trans product. So here Me and here hydrogen. So this is trans product. So see what I want to say that the addition of singlet carbon to olefinic double bonds are stereospecific as mostly exothermic reactions. So singlet cis will give cis product and trans butene will give trans product. Okay, so this is all the singlet carbene because reaction like this here. This are here. One is like this, one is like this. Okay, one is shape. Here two electrons are, one is up, one is down. So pairing. So this up will pair with down, and down will pair with up like this. So you get concerted one. So you got what I said is concerted. The reaction of addition of singlet carbene to double CC double bond is concerted and stereospecific and exothermic. That means cis will give cis product, trans will give trans product. But in the case of triple carbene, this is quite different. It's a bit different. Okay, I'll just show you. Addition of triple carbene. So here let's say singlet. Okay, this is cis. Okay, cis product like methyl, cis to butene, cis reacts with triplet carbene. Okay, let's say triplet. Triplet is one is what are up. Okay, triplet. Triplet carbene here. So addition of triplet carbene to cis butene. But here you have here in this two, one is due to the this one is up, one is down. Okay, pairing like this. So one down will combine with one. Okay, so the first step is formation of this methyl group. Me, and they have formed like this. So you have one up, so one down. These are off now. Okay, Cl. So these are off. Okay, one down is this one down spin down, and one is off. Okay, this down with this one. Interaction by Pauli exclusion principle linked down bring with the up. So we got it like this. Only remaining one is up like this. Okay. So this one undergoes some ISC intersystem crossing by collision one. Okay, collision, some system takes place collision followed by rotation of the bond. So here collision takes place. So this is what we call say intersystem crossing. Okay, intersystem crossing takes place. So due to this angle bond is like this. One is rotated. So you got two types. So here methyl and this CH methyl. So here Cl up. Okay, this is now due to the collision, so it becomes down here plus another one is okay ICl and CCl. Can you see this one? Okay, up here, spin is up, and this one due to some rotation takes place and bond is rotated. So methyl will come here, and this hydrogen here, and this is down. Okay, spin is down. This is methyl group. So here, these two can be combined. So they by Pauli exclusion they can combine. So you can give this will give cis product, Cl. So hydrogen here, it's methyl, so cis product. And here also you can give same product plus this one will give, can you see this one, can give trans. Okay, CCl, methyl, hydrogen here. Okay, so this will give trans. Okay, here trans. So what I want to say that is not stereospecific. So you got an enantiomer of two element which you got one is cis and trans of what I got. So addition of triplet carbene to polyphilic double bonds, we got two products, is isomeric products, receiving mixture of cis and trans. It is different from singlet carbene. So here first process is undergo that one up combine one down to give a link like this. Then it undergo some collisions followed by rotations. So you got these two types. So one that is come to up, come down, here also down, and due to rotation, you got this methyl comes here, hydrogen here. So we got two products. One is cyclization takes place, so like this. So you got two products, Cs and trans. So what I want to summarize this, you can say that addition of single carbon is still specific, giving only one product, and can start that. But addition of triple carbon to double bond compound is not concerted. It gives a racemic mixture, and the Cs or trans, like the Cs and as well as trans particles of gas. So this is about the reactions of carbons. Okay, so now can stop here. But carbons also can undergo addition not only with the carbon-carbon double bonds. They can also undergo addition with aromatic compounds. So for example, I'm giving some examples. So pyrols reacts with this carbon. Okay, here ClCl carbon. So addition of this carbon to the aromatic compounds. First, we got a like double bond addition to double bonds. It gives a cyclic cyclopropane rings. Okay, these cyclopropane rings. Mostly these cyclopropane rings and undergo rearrangement or expansion to give like this. So here to undergo minus ICl. So you got a 6-member ring, from 5-member ring to 6-member ring takes place. So here 1, 2, 3 chlorine here, 3 chloropyridine like this. So I'm giving one example that aromatic compounds can undergo addition with carbons to give addition product, which mostly generally undergo rearrangement. So in here, in this case, pyrrole reacts with carbon to give pyridine, 3 chloropyridine. So here ring expansion takes place from 5-member ring to 6-member ring. Another example I can give, simple benzene also can react with this carbon. Okay. So I'm giving the benzene. Benzene has a double bond types. Okay, first reacts with carbon here. So addition takes place here like this. So here first step is formation of a cyclic propane ring. Okay, cyclopropane form like this. Then ring expansion can take place this way. Okay, this way, this. Okay, you can have from 6-member ring to now it comes to 7-member ring. Okay, 7-member ring. So here ring expansion takes place. So addition of carbons to aromatic compounds give a first product is fused cyclopropane ring, then which can undergo ring arrangement, expansion of the ring to take this from lower to higher ring, 6-member ring. So here in the case of benzene, you got 6-member to 7-member ring. So one example, if you react this with say toluene, okay, toluene reacts with carbon, then we can have three products. So you can have 3 products. Okay. So in the case of reactions of carbene with toluenes give 3 products. So you can try this one or position depending on the position of this methyl groups. So here this carbon can attack here the double bond, or carbon can attack here double bond, or other one like this. So you got 3 types of intermediate. So first intermediate this one, and second intermediate reaction this one. You can say plus this one. So here you got ClCl, this double bond react with methyl group, and this is intact, this double bond, this one intact. Okay. So here this reacted with this one. Another one is the reaction this one. So here the double bond react with this CH3 here, and this Cl, this carbon, and this. So here this double bond intact, the one intact like this. Okay, you got 3 products. First one addition here, and second addition is here, and third addition is this way. So now this can go ring expansion. So you can have these 3 will give ring expansion, will give first one will give, say let's say this one earlier one. So ClCl, and this one. Okay, so methyl group is here. Methyl group will be here CH3. So here the position will be 1, 1, 2, 3. Okay, 1, 2, 3. And another one from here. Okay, we expand this expand this ring like this, like this, like this. Then you can get similar. You can get submembering, solar submembering, but position of this thing is different. Okay, let's say this methyl group here, CH3, then here double bond here, then so here CH2 will be here, so you got here like this. Okay, this is double bond here and double bond here, and this is these two are coordinate. Okay, so like this. Another one from here, you got from this one you get same case, you get this one like the ring expansion. It has made up the double bond takes place to get the ring expansion. So here also same case. Let's say submember ring. Okay, yes, there's a methyl group here. So now here the same one methyl group. Now double bond should be here. Okay, Cl 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 Cl. So here like this. So we got three products like this. So what I want to say that addition of aromatic compounds by these carbenes, if the cyclopropane pass, fuse cyclopropane ring, then undergo rearrangement, or you can say ring expansion takes place. So what I'm giving, toluene give three products, and this pyrrole give one product. Okay, expansion takes place. So this is about it. So now let's come to about the rearrangement of carbenes. Okay, this is about it. These are all about the addition reactions of carbenes to aromatic compound, double bond and double bonds. Now let's come to rearrangements of carbenes. Okay, so carbenes can undergo rearrangements many types. Say like it can undergo like hydrogen 1,2 migration, 1,2 elimination, 1,2 can take place. So let's say 1,2, say, or CO2ET. Okay, let's say CO2ET is carbene. Okay, so yeah, that carbene or CO2ET. So you can undergo rearrangement like this. So like this. So like this. Okay, hydrogen can be 1,2 ship, 1,2 hydrogen ship takes place, rearrangement takes place. So you can get C-1CH, CO2ET. Okay, then alkyl group also can be, sometimes alkyl group can also be, say R can also get like this. R also can undergo migration takes place. Okay, alkyl group 1, 2, alkyl ship, R shift. Okay, so here C-1, C, R, CO2ET. So what I want to set, rearrangement can take place by migration of hydrogen or alkyl group to get this one. The one is the most important rearrangement in the case of carbenes is the iron ester synthesis. And ester synthesis. Okay. Here acyl carbenes are involved. So let's I will write here. Okay. Here iron ester synthesis involves acyl carbenes are formed, which undergo rearrangement to give ketene, then undergo hydrolysis or reaction with alcohol like that. So let's see plus one. This is also rearrangement of carbenes with iron ester synthesis and ester synthesis. Okay, let's come to this one. So here the reaction is usually take two steps. One is the reaction with a benzoyl acyl chloride. Acyl chloride reacts with diazomethane. Okay, CH2 and 2, followed by hydrolysis, or as hydrolysis is 2O in the presence of acid. So you give conversion takes place to get this R, CH2. So you can get another one with water, then you can have acid. So here for this acyl chloride can get from another acid. corresponding acid derived so like this by thionyl chloride. Acid chloride or acid chloride can be obtained by reacting with acid. So what I said that this acid can be converted to higher homologs of the acid, and the CH2 increases by reacting with diazomethane for hydrolysis. So this overall reaction is known as ester synthesis. This reaction involves a carbene. So let's see the mechanism. By mechanism, we can know how carbenes are involved. So first step is reaction of acid chloride mechanism. Let's see the mechanism. Okay. Acid chloride is reacting with this diazomethane. Diazomethane can have two structures like this, or you can have the another resonance structure CH2. This will come and this double bond end like this. Okay, so you can have the attack. So this can attack here, or you can attack this way or this way also like this. So you got first reaction of acid chloride with the diazomethane. You got a this one CH2 diazoketone. Okay, CH2 double bond, and this is a positive charge here. So this attack. It is on triple bond like this. So this by presence of this one, first is remove this one. Okay, this proton is removed. CO, CH, abstract by and double bond end. This ketone carbon group. Okay, so remove by pairs after the proton, loss of proton after the proton. Okay, so this one, and this loss of this nitrogen will give a ketene. Okay, I mean carbene. Okay, CO, CH. A carbene is called. A carbene is formed. It's called. It's going to be acyl. So it's called acyl carbene. Acyl carbene is formed. So for this first step, once acyl carbene is formed, then rearrangement takes place. This will attack. It's like this. Rearrangement takes place. So you got R, CH, double bond C, double O. So you got ketene. So first step is reaction with acyl chloride with diazomethane to give acyl ketene, acyl diazoketone. So you can say diazoketone is formed. Diazoketone. So diazoketone. This is the first step. Formation of diazoketone by reacting with acid chloride with diazomethane is a first step. And second step is lost this one. You got acyl carbene. Acyl carbene will give ketene. So this is second step. The second step is generally known as rearrangement. Okay. So I can write in an elaborate way. Ester synthesis, mechanism of ester synthesis takes place two steps. First step is mechanism of ester synthesis. Takes place two steps. First step is reaction of acid chloride with diazomethane. See the acid chloride, diazomethane. You got diazoketone. The second step is formation of this diazoketone undergo this. Okay, this undergo lost this nitrogen. Got it acyl ketone, acyl carbene. You got acyl carbene. Lost this one. CH. Okay, acyl carbene. So the acyl carbene can undergo rearrangement. So you got this way. So this is got R, CH, double bond. So here double bond here, C double O. So you can see, okay. So you got acyl. This is called acyl ketene, acyl carbene. This is acyl carbene from ketene. Okay. So this second step is known as up rearrangement. Second step is known as oof rearrangement. Oof rearrangement. Okay. So second step. So since once chitin is formed, then can undergo hydrolysis or reacting with ether or with ammonia or this chitin can react with further can undergo reaction with water. So you can get acid, CO2 ions. If you react with alcohol, then you got ester, wolfram ester, so acid. So you form ester. If you react with same reacting with ammonia, you get amide, CH2, CONH2 like this. So once chitin is formed, then you can undergo hydrolysis or alcoholysis or ammonolysis. So the last lecture, for the lecture. So here, like this. Okay. This phenols, they have been presence of chloroform, say cell3, in presence of an alkali some hydroxide is converted to salicylaldehyde. Okay, salicylaldehyde, aldehyde carboxylic acid. So this is known as Reimer-Tiemann reactions. Reimer-Tiemann reactions. So this is one of the important reactions for using this carbene reactions of phenols are converted to salicylaldehyde. So mechanism of the reactions can be like this. So I'll give the mechanism of the reactions. So first, in presence of phenols converted to sodium phenoxide ion, okay, ONA, phenoxide ion, and this second, and one is that, and then chloroforms reacts with sodium dioxide. So first step, second step. So here you got a carbene, so like reaction of carbene, CCl2, so like this. So remove a plus, HCl is removed. So this third step, this phenoxide ion reacts with, I will show here. Okay, third step I'll draw here. Reaction of this phenoxide ion with carbene. Okay, ONA positive charge reacts with this carbene. Okay, this Cl. So here come like this. Here take here. So now this charge is given to this carbene. So here this carbon becomes double bond here. So here hydrogen here. This carbon like this. Now charge given to here, so the carbon becomes negative charge. So this negative charge is the one pick up the proton. So pick up the proton, so like this. So another one. So here OH like this. Okay. So here CHCl. Now this alkali hydroxide group attack here. So one loss. Go here OH group. OH. Okay, then CH, OH here, Cl. Okay, then loss of this HCl will give this product. So this is the simplest mechanism formation of salicylaldehyde. So you can have hydrogen here, carbonyl group here, and here loss of HCl plus HCl. So this is the way, the mechanism for formation of salicylaldehyde from phenol. So here carbon is involved in the intermediate. So phenol reacts with chloroform in presence of alkali gives salicylaldehyde. So intermediate is formation of carbene. Okay. So these are all the reactions of carbene. So I have to cover about carbene story, this thing. So we have discussed carbene, two types of carbene, singlet and the triplet carbene, and their structures. One is more are bent, another one occupied. In the case of singlet carbenes, two electrons occupy the sp2 orbital, but in the case of triplet carbene, you can have two types. One is linear, one is sp2 hybrid structure. In the sp2 hybrid structure of triplet carbene, the two electrons occupied each of these one spin above the sp2, another one in the p orbital. Okay, but in the linear case, these two spin occupied, each of these spin occupied the two p orbitals. So this one. Okay, then. So here we have discussed all these things. So next we'll come to the all these things will come to the next lecture about this thing. So we have discussed generation carbene, then structure, then we have reactions of carbene, then addition reactions, insertion reactions, so some type of RNA synthesis, hematite reactions. So this is all about the carbenes. Okay, let us stop.